Welcome back. Let's talk about power protection circuitry. So what do we mean by power protection circuitry? Let's take one example. We have a battery that we want to connect directly to some sort of controller, maybe perhaps a microcontroller. And maybe this microcontroller is an Arduino or something of that nature, and it performs some sort of function, and it connects to this battery through some sort of connector. The connector will have a receptacle and a plug. Now, what happens if you flip this connector backwards and accidentally connect the plus side of the battery to the negative side of the Arduino or microcontroller by accident? Well, unless the microcontroller has some sort of protection circuitry, it's probably going to blow up. It's not going to work. So on many electrical engineering interviews, interviewers are going to want to know, have you worked with protection circuits before? Do you know how to stop things like this from happening? So let's take a look at a typical power protection interview question. Design a circuit that provides reverse polarity protection, which is exactly the scenario we just talked about, for a battery plugging into a resistive load. Give two examples, one a low-cost solution and one more intricate. So there's various different ways we can do this. The obvious way is to, of course, use a diode, because diodes only allow current to flow in one direction, and if you plug in a battery in the opposite direction, current won't be able to flow, and therefore you can save the load. That's exactly what we'll look at as our first solution. We have a battery with a certain voltage across it, and before it reaches the load, we'll put in a diode in series with the direction that we anticipate the current to flow. This is a Schottky diode, so it has a low dropout voltage, approximately 0.3 volts. And if we plug the battery in the forward way, current will flow through the Schottky diode and to the load after dropping 0.3 volts across it. If we plug the battery in the opposite way, current will not be able to flow in this direction and therefore won't be able to complete the closed circuit. Because of that, the load will not have a voltage drop across it and therefore won't be damaged. Now, this is a really low-cost solution because all you need is a single diode, and we know from previous lectures that diodes are super cheap. But this has one pretty serious and major flaw, and that's, of course, this voltage drop. If you want a, let's say, 3.7 volt lithium-ion battery to connect directly to this load, you're never actually going to get that full voltage. You'll get 3.7 minus this voltage drop. So it's not really great because you don't see the appropriate voltage at the load, and you also burn through thermal power and reduce your efficiency by the formula P equals IV. So you'll burn 0.3 volts times whatever current you're putting through this diode in terms of heat, and that will reduce your efficiency. But for low-cost solutions, this is pretty good. But if we want a more intricate solution, let's take a look at the next example. In this example, we are using a battery and connecting it directly to a P-type MOSFET, where this is the source, this is the gate, and this is the drain. Now here I've also modeled the MOSFET's body diode that is in parallel with the drain and source terminals of the MOSFET. So all of this is actually internal to the MOSFET. We're not adding an external diode. Basically, the way that this system works is if you plug the battery in the right way, initially the MOSFET is off, so current is not going to flow in this direction. You are not going to get current in that direction. What will end up happening is the current will initially go through this body diode, which will have approximately 0.7 volts of drop across it. So let's say that this is a 9-volt battery. You'll immediately get 8.3 volts at the source. When that happens, the MOSFET will turn on because the gate is grounded. And therefore, your VSG is going to be 8.3 volts, which will turn on the MOSFET. As the MOSFET turns on, the source voltage will increase up to the full or very close to 9 volts, because instead of current going through this body diode, it's now going to go through the MOSFET itself, which of course it does have some sort of on resistance in series, but that is much, much smaller than, it will have a much, much smaller resistance and voltage drop across it in comparison to the diode. Therefore, this 8.3 value will get up very, very close to the full 9 volts. VSG will go up to 9 volts and will keep this MOSFET on. Now, what happens if we plug in the battery in the reverse direction, where we have plus here and minus here? Well, first things first, no current flows into the gate of a MOSFET, or very little current, so not a lot are going to go through there. The current will try it to go through the load, but the MOSFET is off. So no current is going to go through the MOSFET. Current will try to go through the diode, but the diode is blocking it, and therefore we have no current going. The gate and source of the MOSFET will be at the exact same voltage, so VSG will equal 0. And since VSG is equal to 0, the MOSFET will stay off. There is no way to close the circuit with reverse polarity protection here, and therefore we have protected our load from having any current go through it. Great! So we've successfully done reverse polarity protection. In the next lecture, we're going to talk about solar cells, which are a really hot new topic.